In section 5.7, we look at partial fractions. First, let's consider an example. Suppose we wish to add the two rational expressions 5 over x minus 3 and 6 over x plus 2. We know that in order to do this, we need to get a common denominator, and we know the least common denominator here is x minus 3 times x plus 2. So to do this problem, we would take the fraction 5 over x minus 3, and we would multiply the numerator and denominator by x plus 2. And we would take the fraction 6 over x plus 2 and multiply the numerator and the denominator by x minus 3. Then we would go ahead and do the multiplication. So in the first fraction, we have 5x plus 10 over the common denominator. And in the second fraction, we have 6x minus 18 over the same denominator. And finally, we would add these fractions together, since they now have a common denominator, and we would just combine like terms. So 5x plus 6x is 11x, and positive 10 plus negative 18 is negative 8. And so we end up with the rational expression 11x minus 8 over the product of x minus 3 and x plus 2. So this is just a matter of combining two rational expressions using addition. What we want to talk about in this section is, what if we started with this fraction and we wanted to look at its partial fractions? And usually this is called a partial fraction decomposition. So the question is, if I gave you this fraction, how would you break it down into the sum of these two smaller partial fractions? So in this section, we're going to talk about that process. So in the first case, we're going to consider a denominator where all of the factors are linear factors and they are all distinct, which means they are all different. So if we have a rational function p of x over q of x, where p of x and q of x are polynomials, and the degree of p of x is less than the degree of q of x, and if we let all of these a values and b values be real numbers, and if q of x is the product of these distinct linear factors, then there exists real numbers a1 to an such that the partial fraction decomposition of r of x is the following. Now, I would expect you to listen to what I just read and absolutely not understand any of this, because it's really complex with all of these subscripts and variables, etc. So let me give you a couple of really simple examples. Suppose we had the following fraction. 3x plus 4 over x plus 5 times x minus 3. What I would like to do is break this apart into its partial fraction decomposition. So what you can see here is the denominator is composed of two factors. They are each linear factors, and they are both different from each other. Basically, what this tells us that you can do is you can break this down into the sum of two smaller fractions, where the first denominator will be x plus 5, and the second denominator will be x minus 3. Now, the only question is, what numbers would go in the numerator? Well, those need to be determined, and that's what they call these a values here. So what we typically do in a problem like this, when we set it up, is we'll just say that we don't know this first value in the first fraction, so we'll call that capital A. And we don't know the numerator of the second fraction either, and we'll call that capital B. This is what we typically use instead of using these subscripts. Now, the whole thing you would have to do here now is solve for a and b. And we'll talk about how to do that in just a couple of minutes. Let's consider another example. Suppose you were asked to find the partial fraction decomposition of this rational expression. And I want to point out that the degree of the denominator is larger than the degree of the numerator, and that needs to be true for all of the problems that we do in this section. But if I'm going to find its partial fraction decomposition, the first thing I need to do is factor the denominator. So I want you to notice that in the denominator here, one thing you can do is you can factor out an x. Oops, let me put an x here. That there should be an x in this spot. There we go. So I can factor out an x, and if I do that, we get x squared minus x minus 6. And then we can factor what is left over here, and that's going to give us x times x minus 3 times x plus 2. That is the complete factorization of the denominator. So if I put that in here now, you should notice that this denominator is composed of 3 distinct linear factors. So distinct just means they're all different, and linear means that they are all x to the first power. So because we have 3 distinct linear factors, when we break this up into the sum of our partial fractions, each one of these fractions is going to contain a single factor from that denominator. So the first fraction will have an x in the denominator, the second one will have an x minus 3, and the last one will have an x plus 2. And now the only question is, what are the numbers in the numerator? Well, we don't know those, so we're going to call those a, b, and c. And then we would have to solve for a, b, and c to get this partial fraction decomposition. All right, now let's take a look at an actual example where we are going to find those coefficients. So here we want to compute the partial fraction decomposition of the fraction 5x minus 7 over x squared minus 4x minus 5. So the first thing I'm going to do is I'm just going to factor the denominator. We need to know what factors is it made of. So x squared minus 4x minus 5 is relatively straightforward and simple to factor. If you do that, you should get x minus 5 times x plus 1. And now we know that we can set up the partial fraction decomposition here to have the sum of 2 fractions, where the first fraction will have the factor of x minus 5 in the denominator, and the second one will have the factor x plus 1 in the denominator. And we don't know what the numerators are going to be, but we do know that they're going to be numbers. We just don't know what those numbers are. So I'm going to call the first one a and the second one b. So now let's go ahead and take this equation and let's solve for a and b. So one of the ways we solve for a and b here is we're just going to get rid of the fractions by multiplying both sides of this equation by the least common denominator. So I'm going to multiply both sides by x minus 5 and x plus 1. Now on the left-hand side, when you multiply, these factors simply cancel out, and all we have left over is 5x minus 7. On the right-hand side, we're going to distribute these factors to each one of these. And when we do that, we get the following. And what happens when you distribute is you're going to get some cancellation. So here the x minus 5 will cancel, and here the x plus 1 will cancel. And we end up getting 5x minus 7 is equal to a times x plus 1 plus b times x minus 5. Now, to solve for a and b, there's a couple of different ways that we can do it. The easiest way to do it is to simply let x be equal to some number, And good numbers to choose are numbers that make these factors equal to 0. So for example, if I choose x equals 5, on the left-hand side we get 5 times 5 minus 7. On the right-hand side we get a times 5 plus 1 plus b times 5 minus 5. And this is the beauty of it. 5 minus 5 is 0, and b times 0 is 0. So this goes away. And what we end up with, on the left-hand side, we have 25 minus 7 is 18. And on the right-hand side, we have a times 6, which is 6a. And if you solve for a here, you get a is equal to 3. Now we do the same thing, but we pick the value of x that will make the other factor equal 0. So if I choose x equals negative 1, on the left-hand side, we get 5 times negative 1 minus 7. On the right-hand side, we get a times negative 1 plus 1 plus b times negative 1 minus 5. If we do the math here, we get negative 12 is equal to, this cancels out, and then we get negative 6b. Dividing by negative 6 on both sides, we get b is equal to 2. Once we have the values of a and b, we simply need to take these values and plug them back in here, and that is our partial fraction decomposition. So when we plug in a equals 3 here, we get 3 over x minus 5, and when we plug in b equals 2 here, we get 2 over x plus 1. So the fraction 5x minus 7 over x minus 5 times x plus 1 decomposes into the sum of these two fractions. And I will just say a little word here. You may not know why you're learning how to decompose fractions into smaller fractions, but trust me when I tell you it's an important skill to know for calculus. The next case we take a look at is the case where the denominator has at least one repeated linear factor. Now what that means is you have a linear factor that occurs more than once. Let's consider the following example. 3x plus 2 over x squared minus 10x plus 25. So if I'm going to find the partial fraction decomposition for this, the first thing that I would do is I would factor the denominator. X squared minus 10x plus 25 factors into x minus 5 times x minus 5. So notice that these two factors are the same. This is what we mean when we say that it has a repeated linear factor. We have the same factor occurring twice. Now I can also write this as 3x plus 2 over x minus 5 to the second power. And that's what you see here, right? Up here it says that q of x, the denominator, has the form ax plus b to the m power, where m is some number bigger than or equal to 2. So that just means that you have that factor and it's repeated this many times. So how do you set that up? Well, the decomposition is going to be set up by writing every power of that factor up to the number that you have. So when we break this down, our first fraction is going to have x minus 5 to the first power. And our second fraction is going to have x minus 5 to the second power. And that's where we stop for this one because there are no other powers of that, right? In other words, second power is as high as it goes. And then we know that there will be some number here, a, and some number here, which I'll call b. And then you would solve for a and b accordingly. Let's consider another example. So here we have the fraction 5x squared plus 3x minus 4 over x minus 3, that's to the first power, times x plus 4 to the third power. So here we have a distinct linear factor, x minus 3. It's not repeated because the power here is 1. But then the other linear factor, x plus 4, is raised to the third power. So what would the partial fraction decomposition look like for this? Well, in the first fraction, we're going to have to represent the x minus 3 factor. In the next three fractions, we need to express the x plus 4 to the third power by putting x plus 4 to the first power, x plus 4 to the second power, and x plus 4 to the third power. And then in the numerator, you're going to have 4 constants that you need to find. So we'll call the first constant A, the second constant B, and then C, and then D. And then you would have to solve for these. So this is how you set up the partial fraction decomposition when you have repeated linear factors. So in this example here, we are asked to write the partial fraction decomposition of the fraction 4x squared minus 7x plus 1 over x cubed minus 2x squared plus x. So the first thing we need to do here is we need to factor the denominator. So let's go ahead and see how we can factor this. Well, first of all, you can see that we can pull out an x, and when we do that, what you have left over is this. And then we can continue factoring, and this one's relatively simple. We end up with x times x minus 1 times x minus 1. So notice that we have a repeated linear factor here. So I can write this as x times x minus 1 to the second power. So now what I need to do when I break this down, I need to have 3 fractions. The first fraction is going to represent the factor of x. So we're going to have some number a over x. And then the next 2 fractions are going to represent x minus 1 to the second power. So we have x minus 1 here and x minus 1 squared here. And then we have unknown constant b and c. So now what we need to do is solve for a, b, and c. And this is very similar to what we did before, but it's just a little bit different in one aspect. So the first thing I'm going to do is multiply both sides by the least common denominator. So I'm going to multiply both sides by x and also x minus 1 squared. And doing this is going to get rid of all the fractions. On the left-hand side, it's very straightforward. The factors here cancel out, and we are left with 4x squared minus 7x plus 1. On the right-hand side, when we distribute here, you should be able to see that the x factor here and the x factor here are going to cancel out, but we have the a left over, and we also have x minus 1 squared left over. So we have a times x minus 1 squared. When we distribute here, the x minus 1 is going to cancel one of these factors, and what we'll have left over is b multiplied by x and multiplied by the one factor of x minus 1 that is still left over there. And finally, when we multiply here, you can see that the x minus 1 squared is going to cancel out this factor, and we get c times x. All right, so now we've gotten rid of all the fractions. Now we can solve for a, b, and c. Now what I can do is I can let x be equal to 0. If I let x equal 0, notice that this factor cancels out because c times 0 is 0. And this factor also cancels out because b times 0 times whatever is 0, right? So when you plug in 0 here, these cancel out. When I plug in 0 on the left-hand side, I just get 1. And when I plug in 0 here, I get a times negative 1 squared. And so this says that 1 is equal to a. So we've solved for a. Now what's the next value of x that I'd like to use? Well, I want to use a value of x that's going to cancel this other factor. So I'll plug in x equals 1, because 1 minus 1 is 0. So if I plug in x equals 1, this factor is going to cancel out, and this factor is going to cancel out, and all we're going to have left over is c times 1, which is c. So on the right-hand side, we just get c. And on the left-hand side, we have to plug x equals 1 into here. When you plug in 1 here, you get 4 times 1 squared, which is 4, plus 1 is 5, minus 7 times 1 is 5 minus 7, which is negative 2. So we get c equals -2. Now, there are no other factors that will cancel out by simply plugging in a value of x. So how do we find out what b is? We just plug in any other value of x that we want. Now, I would recommend trying to plug in as small a value for x as you possibly can. So since I've already used x equals 0 and x equals 1, let's use x equals 2. If I plug in 2 on the left-hand side, we get 4 times 2 squared minus 7 times 2 plus 1. And if I plug in 2 on the right side, first of all, we know a is 1 now, so we can put 1 in for a. And if I plug in x equals 2, we get 1 times 2 minus 1 squared. Now, we don't know what b is. That's what we're trying to find out. So b stays b, but x is 2, so we get b times 2 minus 1. Plus, we know c is -2, and that's going to be multiplied by x, and we're letting x equal 2. So I'm going to have -2 times 2. Now we just need to do the math here. So 4 times 2 squared is 4 times 4, which is 16. Take away 14 is 2 plus 1 is 3. So we get 3 there. Here we have 1 squared, which is 1 times 1, so that's 1. Plus, we have 2b, right? Do the math here. And then we have -2 times 2 is -4. So we have 3 equals 2b minus 3. Add 3 to both sides, we get 2b equals 6, and this means b equals 3. And once I've solved for a, b, and c, we now have the partial fraction decomposition. All we have to do is take those values of a, b, and c and plug them in here, and that's the answer. So let's go ahead and do that. So substituting these values into here, we get the following partial fraction decomposition. So what is this fraction equal to? It's equal to 1 over x plus 3 over x minus 1 plus -2 over x minus 1 squared. And one final note here, if one of your values turns out to be negative, like this one here, you can put plus the negative, but another way you can do it is you can just change that negative sign, or excuse me, change that positive sign to be a negative sign. So you can put that negative that was in front of the 2 out in front of the fraction. This is a little bit cleaner. Now let's consider case 3. In case 3, the denominator has at least one non-repeated irreducible quadratic factor. So we have to describe what does it mean for a factor to be an irreducible quadratic. So ax squared plus bx plus c is a quadratic factor. What does it mean to be irreducible? Well, let's just take a couple of examples. If I give you x squared minus x minus 6, this is reducible because we can factor it into x minus 3 times x plus 2. If I give you x squared minus 9, this is reducible because we can factor that into x minus 3 times x plus 3. And even if I give you x squared minus 5, this is also reducible because you can factor it into x minus radical 5 and x plus radical 5, right? Because remember, if you set x squared minus 5 equal to 0, you get x squared equals 5, and by taking the square root of both sides, this is going to give you x is equal to plus or minus the square root of 5. And we know from our discussion about zeros and factors that if these are your zeros, then your factors are going to be x minus radical 5 and x plus radical 5. So these are all examples of reducible quadratic factors. So what does it mean to be irreducible? What it means is that the quadratic cannot be factored over the real numbers. So what it means for a quadratic factor to be irreducible is the zeros are non-real, right? So in other words, they involve imaginary numbers, complex numbers. So an example of an irreducible quadratic factor would be something like x squared plus 9. Because if you set x squared plus 9 equal to 0 and solve for x, you get x squared equals negative 9, and then taking the square root of both sides gives you x equals plus or minus 3i. So notice that the zeros here are non-real, and that means if you tried to factor this, x squared plus 9 would be x minus 3i times x plus 3i, right? And this is what we mean when we talk about being irreducible, because we have to use complex numbers to factor it. So because this is the only way to factor x squared plus 9, we would say x squared plus 9 is irreducible. So what does it mean to be irreducible? It means the zeros are not real, right? Meaning that they are complex. Let's take a look at another example. So in this example, we're just checking to see if this factor is an irreducible quadratic or not. And what we have is 2x squared plus x plus 3. So first of all, you might just try to factor this. You can use the magic x. You could say 2 times 3 is 6, and we have a positive 1 in the middle. Are there any factors of positive 6 that will add up to give us positive 1? And the answer is no, right? Like if I pick 3 and 2, 3 plus 2 is not 1. If I pick negative 3 and negative 2, negative 3 plus negative 2 is not 1. The only way I'd be able to get 1 is if I maybe change this to be a positive 3 and a negative 2. So when I add these, I get 1, but the problem now is 3 times negative 2 is not positive 6. So you can try all you want, but you won't be able to factor this in the traditional sense. So let's see what's really going on. If we set this equal to 0 and we solve for x using the quadratic formula, we get x equals negative 1 plus or minus the square root of 1 squared minus 4 times 2 times 3 divided by 2 times 2. And this is negative 1 plus or minus the square root of 1 take away 24 divided by 4. And this is negative 1 plus or minus the square root of negative 23 divided by 4. And right here you can see that you are taking the square root of a negative, and this is non-real. So what that means is this equation has non-real solutions, and if it has non-real solutions, that means that this factor has non-real zeros, and that means it is irreducible. So 2x squared plus x plus 3 is irreducible. All right, now let's go back to the irreducible quadratics. So if we have an irreducible quadratic, the next question is, what do you do about it? How do you break it down? Well, the way you break it down is you take that irreducible quadratic, whatever it may be, but now the numerator is not just going to be a constant. It's going to be a first-degree polynomial. Because since your denominator is a second degree, if this fraction is proper, that means the degree of the numerator has to be less than the degree of the denominator, which means you could have a first-degree polynomial in the numerator. So when you have an irreducible quadratic factor, you do not simply put a in the numerator, you have to consider something like ax plus b. Let's take a look at an example. So in this problem, we want to find the partial fraction decomposition of 3x squared minus 2x plus 13 over x plus 1 times x squared plus 5. So they have done the factoring for us, which is really nice. And I want you to notice that x plus 1 is a regular linear factor, and x squared plus 5 is an irreducible quadratic, right? Because if you take x squared plus 5 and set it equal to 0, you can see right away that when you take a square root here, you're getting the square root of a negative, which means that the zeros are complex. All right, so that is an irreducible quadratic factor. So now what this means in terms of breaking it down is in our first fraction, we're going to have x plus 1 on the bottom. Now that's just a regular linear factor, so that means we'll have the number a in the numerator. And then for the second fraction, we will have x squared plus 5 in the denominator. This is an irreducible quadratic, which means the numerator has to be a general linear factor. So it's not just b, it has to be bx plus c. And now what we need to do is solve for a, b, and c to figure out the partial fraction decomposition. So to do that, we are going to multiply both sides by the least common denominator. So when we do that, on the left-hand side, we get nice cancellation here. So we have 3x squared minus 2x plus 13. And on the right-hand side, when we distribute here, we can see that the x plus 1 cancels out the x plus 1. So we have a times x squared plus 5 left over. Plus, and when you multiply the second term here, we're going to have x squared plus 5 cancels with x squared plus 5. And that means we will have bx plus c multiplied by x plus 1. Now, this is a little bit more complicated in terms of finding your coefficients. So we're going to talk about how to do that now. When you have an irreducible quadratic, the best thing to do is to multiply everything out. So on the left-hand side, we have the same thing as before. But on the right-hand side, if I multiply this out, I'm going to have a times x squared plus 5 times a. And then here, if I multiply this one out, we're going to have bx squared plus bx times 1, which is bx, plus cx plus c times 1 is c. Now what I'm going to do on the right-hand side is I'm going to group together all the like terms. So the like terms would be ax squared plus bx squared. Let's put those together. Next, I'll group the x terms. So we have a bx plus a cx. Let's write those together. And finally, we have the constant terms, which is 5a plus c. Now, the reason I do this is because in each one of these, I can factor out the variable. So in the first one, if I factor out the x squared, I'm going to have a plus b times x squared. And in the second one, if I factor out the x, I'll have b plus c times x. And the third factor, there's nothing, the third term, there's nothing to factor out. We'll just leave that one alone. Now here's the underlying principle. If the polynomial on the left side is equal to the polynomial on the right side, then the coefficient of x squared here must be equal to the coefficient of x squared there. So what that means is that a plus b must be equal to 3. Likewise, the coefficient of x here, which is negative 2, must be equal to the coefficient of x here, which is b plus c. So we know that b plus c must be equal to negative 2. And finally, the numerical term here, which is 13, must be equal to the numerical term on the other side. So 5a plus c must be equal to 13. This is a system of equations with 3 variables. Now what we need to do is simply solve that system. Now this can be a little bit weird because you'll notice that some of the equations are missing some of the variables. But all I need to do is think in terms of elimination. So let's take the first 2 equations. If I multiply the second equation by negative 1 on both sides, this is going to give us a plus b is equal to 3. And the second equation is negative b minus c is equal to 2. Now, if I rewrite this, I can say a plus b equals 3, And instead of saying negative b minus c, I can say negative c minus b is equal to 2. And now you can see that if you add these two equations together, the positive b and the negative b cancel out, and we get a minus c is equal to 5. So what I did there is I got rid of the b. Now, why is that a good thing? Well, if I take the last equation here and I put it together with this equation, you can see that we get a little bit lucky here. If we add these together, the c's cancel out and we get 6a is equal to 18. And that means that a equals 3. Now, once I have a, it's very easy to find all the other values, right? So for example, if I know that a is 3, just take that first equation. A plus b must be 3. Well, but if a is 3, then that says 3 plus b is 3, and that means that b has to be 0. And then if I know that b is 0, I can take the second equation, b plus c is equal to negative 2. But if b is 0, that means 0 plus c is negative 2. So c must be negative 2. And now you can see that I have all three values for a, b, and c. So a is 3, b is 0, and c is negative 2. And that means I can come back up here and I can plug those values in to get the partial fraction decomposition. So the final answer here, a is 3, so we're going to have 3 over x plus 1, plus b is 0, so this is 0, and c is negative 2. So what we have is negative 2 over x squared plus 5. And we can rewrite this finally as 3 over x plus 1 minus 2 over x squared plus 5. And that is the partial fraction decomposition. The last case is the case where you have repeated irreducible quadratic factors. And this is not terribly difficult to understand because you do the same thing that you did with repeated linear factors. And that is you have to have a denominator up to the power of the repetition. Let's take a look at an example. So here we want to find the partial fraction decomposition of this really large fraction. Notice that the denominator is a repeated irreducible quadratic. So x squared plus 3 is irreducible, and it is raised to the second power. And so what that means is we're going to have our first fraction, we'll have a denominator of x squared plus 3, and our second fraction will have a denominator of x squared plus 3 squared. Now these are irreducible quadratics, so the numerator here needs to be ax plus b, and the numerator here needs to be cx plus d. So each one of these is a linear factor, and we need to make sure that all these coefficients are represented by different letters, and so what we typically do is just go in alphabetical order. And now we have to solve for a, b, c, and d. So we're going to multiply both sides by the least common denominator to cancel the fractions. So on the left-hand side, these cancel out, and we end up getting negative 2x cubed plus x squared minus 6x plus 7. And on the left-hand side, when you multiply here, we are going to have ax plus b. And this is going to cancel one of these factors, so we will still have this multiplied by x squared plus 3, plus, and then when we multiply here, this denominator completely cancels this out, and we just end up with cx plus d there. Now I'm going to multiply this out, so we have same thing on the left-hand side. And over here, when we multiply this, we get ax to the third power plus bx to the second power plus 3a times x plus 3b plus cx plus d. I'm going to collect all the like terms here. Now, we don't have a lot of like terms, but these two terms are x's. I can group those together. and these two terms are constants. So if we group those together, we get the following. And now we can rewrite this as ax cubed plus bx squared. Right here we can factor out the x, and we get 3a plus c times x, and then we have plus 3b plus d. This looks awful. I would agree with that assessment. But it's actually not bad at all, because the coefficient of x cubed on the left side is -2, and the only coefficient of x cubed on the right side is a. And so that means a must be equal to -2. The coefficient of x squared on the left side is 1, and on the right side it is b. And so that means that b must be 1. And then the coefficient of x on the left side is -6, and the coefficient on the right side is 3a plus c. But the good news here is we know what a is, right? A is -2, so we can put that in here. And that is going to give us -6 equals 3 times -2 plus c. And this says -6 equals -6 plus c. And that means that c is 0. And finally, the constant term on the left side is 7. And the constant term on the right side is 3b plus d. But a bit of good news again, b we know is 1, so we can put in b equals 1 here. And that gives us 7 equals 3 times 1 plus d, or 7 equals 3 plus d, and that means d equals 4. And so we have found a, b, c, and d. Now we just take all those values and plug them back in up here for a, b, c, and d, and that will be our partial fraction decomposition. So if we do that, we get this. And this is our partial fraction decomposition. So once again, all we're doing here is we're taking a equals -2, and we are plugging it in right there. We're taking b equals 1, plugging it in right there. So that's -2x plus 1 over x squared plus 3. And then c is 0, so that goes away. D is 4, so we have 4 over x squared plus 3 squared. And that's how we arrive to this decomposition.